Good evening, everyone. Today we're going to be doing a fairly similar video to what we've done previously. So we're going to be doing another code review, and we're going to be reviewing the same task as previously. So I just recently did a code review video where we reviewed an implementation of this word task made with Scala. So today we're gonna do the same thing, except it's gonna be implemented with C#. And we're gonna review the code and we're gonna improve upon it and so forth. So for those who have seen the previous video, you can skip to the next section. For those that did not, I very much recommend you to watch that video as well. You will find the link in the description below, and I'm gonna present what the task is before the code review. So the rules of the task are such. It is a card game, and you're playing with a full playing card deck without jokers. And at the start of the game, a trump suit gets selected. So you just select a trump suit randomly out of the 4 available suits, which are hearts, diamonds, clubs, or spades. Then we shuffle the deck and split it in half. Each player gets half of the cards. And then we play in turns. And each turn consists of both players, they just reveal their topmost card from each of their respective decks. We compare the card values. So the cards are compared by their rank. From the lowest one being 2 all the way up to ace. But trump cards are always higher than non-trump cards. So a player with a higher ranking card gets both cards and sets them into a separate pile, which is called a score pile. And if the cards are of equal value, so both are non-trump cards or both are trump cards, and their rank is the same, then each player just gets the card back to his own score pile. And we play this game until both players do not have any cards left, and at the end of the game, the winning player is the one who has more cards in their score pile. So if we have the same number of cards, it's a tie. That's basically the rules. I want to reiterate again that trump cards are always higher. So that means when comparing cards, we first see, if one is a trump and if another one is not a trump, then that card automatically loses. And then, only then, you compare using the ranks of the cards. So with that in mind, we can go into the actual code review. So yeah, let's go into the review.
Right, I will warn you, currently the Discord stream quality is too bad for me to make out any text.
Okay, how about now?
I think you can, it's doing all right. I think you can specifically set the stream to be more text legible, so it'll drop the FPS like mad and it'll focus on the quality.
It's a bit of a problem because I'm not sharing the screen on my side, so it's just a camera, but yeah.
Right.
Can you read it, Phil?
Let me try full screen to see if that helps. After a few seconds, it's usually okay, but not always. Yeah, I can read it now. There we go.
Okay, excellent. So let's start again by looking at the card definition first, because that's the most important piece of data that we have, which is the base building block of our game. And here we have the 3 parts, which is a suit, a rank, and a card. And the first thing that immediately strikes me is that this is a suit. In general, what you want to do is you want to make sure that illegal states are not representable. And currently, nothing really prevents me from doing something like this, right?
This is where I try to bring in the sort of standard, I guess, I don't have a proper word, I'll just say library. Because a card with the Hello Kitty suit, that would still be a functional card. It's just not a standard one.
Yes, but as a counter argument to that, so think about this. In your case, right, you are depending on the name, probably somewhere. Well, maybe not here, but in any sort of program, you would probably like to visualize it, for example, right? If you have a graphical user interface to this logic. And then you need to know how do you do that. And the point of this is, yes, it is open to extension. The problem is that now every part of your application needs to be open to extension as well. And when you think about it and when you actually work with stuff, if you're designing openness to extension, then you have to design for it explicitly. And most of the time, if you have something that is open for extension, then you open some code base and you see, oh, there's a suit. And you say, is there, a place in the code base where this custom suit is actually used? And then you say, no, there's not. But you still have to handle all of that possibility of having a custom suit, in the code base. At every use site that you will write for the rest of the application's life, you will have to deal with that. Usually that's not a trade-off that is worth this possibility of extension. And actually there's this principle of extreme programming, which is called YAGNI, which is an acronym for you ain't gonna need it. So the idea is just write code for the exact specific problem that you're trying to solve. And then if you will need to build upon it, extend it, you will be able to do so. Most of the time, the predictions that we make are terrible, and usually this sort of stuff comes from people fearing refactoring a bit. It is exceptionally prevalent in dynamic languages where it's very hard to refactor because the tools do not know much about your code base and what type the variables are and where things should be changed. But even in this case, people tend to do this, let's keep it open for extension later, and that never comes, but you are always paying the cost of handling that openness. And most of the time, people do not handle that openness. They just do what people do and be lazy, and they just say, oh, yes, there is a possibility for a custom suit to appear, but I know that it will never be custom, and therefore they will just, do like an if statement with 4 cases or something like that, and they will say, that's fine. So with that in mind,
fair.
Yeah.
This is where one of the compromises I did came in, because what I initially tried and couldn't quite get working was making a sort of a sub, I guess, record in this case, not subclass, of a standard suit. With card primarily, but the same sort of idea of anything that can take card can take a standard card, in this case suit, but that standard suit is ensuring validity amongst those 4 known standard suits. So that way you can still pass it around as a known diamond, club, heart, spade, whatever. But if you do have anything that can accept just any sort of suit, it can take that as well just fine. And it leaves that extensibility in while allowing you to keep it down. If something would have trouble extending it, you can just do it to standard suit only.
Well, again, the real question is, do you need the extensibility?
It is more work no matter what. That's true.
Because you can just rewrite this as spades and what?
I did do that initially, and I get very funny with enums because you can define numbers beyond what you actually put with corresponding names.
Okay. Sorry, what did you say?
I'm a little funny with enums like this because initially I did try use them, but I know you can very much have a suit enum with a number outside of those four.
Yes, in theory you can do that by taking any number and just casting it to the suit, and the compiler and the runtime will not stop you. But there's on one side, it's kind of malicious behavior, right? To do so, if you actually do it, you will probably not encounter code that does that in your code base. So I'm not sure that's really a worry that you want to worry about. Unless you're deserializing it from somewhere or something like that, then you can do something like this. What we would do, then we would go like create a helper class. It can be the same name because then it clashes with the enum. So we just add an underscore to it. And then we say, public static option of suit, like from integer, right? And then you would do a switch statement here and say, okay, if it's 0, then it's hearts.
Right, so having a function to sort of filter out any invalid values.
Yep. Then you would say clubs. Let's say
this probably is a good example of where I'm a little unsure on one of the more principal things with functional. When it's having types ensuring validity, how much of that is that you cannot have it be wrong, and how much is saying that this is not expected to be wrong?
So it depends on the language that you're using. If you're using C#, it's gonna be a lot more of I expect it not to be wrong. Like there's gonna be a lot of these presumptions that, for example, in C#, everything is potentially implicitly nullable unless you turn on the explicit nullability option in the newest C#. But you would say, oh, we're not gonna actually pass null anywhere. Where if it's null, it should become an option. So with these things, also there's like in theory you can take an integer and cast it to suit, and then that value will not be one of these values. But in practice, you do not guard against it because the only way for it to happen is for someone to do that kinda maliciously. So you can always screw up things if you're malicious.
That's the fair stance.
Yeah. So with the rank, again, there's the same thing here because we only have a certain amount of ranks. So this also kind of becomes not needed. Yeah, we do have all of these, which are standard ranks. So let's replace them with enums as well.
This I also tried and did it for another reason. You're putting an underscore, right?
Yep.
It infuriated me to no end, but you cannot name something a number, but I get why.
Yep. So yeah, then these are not needed as well. And regarding, I don't know, let's keep it like this. And then we can say, yes, this is a deck. It says the modifiers are in the wrong order. Anyway, yeah, so here we can actually express this using LINQ. So we can say let rank in enum. Wait, let me remember. So is it enum dot get values suit. So we can do this, and then select new card, suit rank. And then it says this whole thing is enumerable, so let's just turn it into an immutable data structure. So to, let's say, immutable array. Yeah, it just now says. So it's fairly a bit more expressive, right? Okay, so we have the definition of the deck and the cards. Let's take a look now at things. So what shall we look at? Program?
Program is where all of the business is happening, so that's probably a good point.
Yeah. Okay, so this can be replaced with, again, this. We usually just use var for the left side. And yeah, so here you have a player, and it has a mutable dictionary inside of it.
Yes, the way I saw it, and I've been a bit unsure with the player in this because it doesn't really come into play at all. It's just sort of a nice abstraction of it is holding the thing in theory. But the player I did not see is intrinsically tied to the game war as much as it is just to card games. This probably comes back to that extensibility again. And so I put a dictionary so you can say, okay, whatever card piles it has, just give it a name and give it a pile.
Still, so the problem here is, so it says read-only record. And the record, essentially what records are immutable data structures. So this thing is not immutable, right? It is very much mutable.
So it's more a promise of immutability than actually enforcing it.
I mean, well, what do you mean by that? By record?
Well, if this record is immutable but is actually in practice still very mutable.
So when you write record, it will create a constructor, it will implement a quality, hash code to string, etc., etc. But it does that from the constructor parameters, which there are 0.
Right.
So what you want to do here is you want to make this into actual proper record by using an immutable data structure, a map here. And here, well, it says there's card piles. Okay, let's go back a bit. So let's take a look at this. right? And I don't know anything about the code, right? It's the first time I've opened it. I take a look at this, and I have absolutely zero idea what this is. This is one of the...
It is a bit funky.
What?
It is a bit funky.
Yeah. The problem is that this can be anything, right? Absolutely any string. And this is an array of cards. So, it doesn't really communicate anything to the person that's reading it. So what I presume you have here is, again, this probably contains two things, right? Which one of the things are the current cards and the other is the score pile, right? And with that, you can just as easily, even if we're doing things mutably, you can just as easily say it explicitly instead of having this.
Yeah.
Because this says there might be 0 card piles, there might be 2,000 card piles. This says
maybe a little too extensible to say, yeah, you give it card piles. It doesn't particularly care. Probably fine to say, yeah, we're only playing war. We know how many piles there are.
Exactly. And with this, you can then transform it into an immutable version of it. So let's transform it. Wait, I always forget what collection types does this thing have. Does it have vector? Let's not worry about performance right now. Let's just call it a sequence. So what you can do is you can say, here's this, there's an immutable sequence of cards, and then there's also an immutable sequence of scored cards, right? And now this is a record because all of the content here is immutable. You
Fair enough.
You can actually compare two players, and if their contents are equal, then the records are equal. While previously, with mutable data structures, you cannot really compare them by their contents, because if you can mutate something, then the identity of the object really matters. If you have, let's say, two video game characters at the exact same coordinates with exact same health, etc., right? They're still not interchangeable because you might have a reference to one of them somewhere and you can change one but not the other. So
I thought since the dictionary was comprised of two immutable, I'm actually just assuming a string is mutable. Yeah.
No,
well, I was assuming that because of the contents, the dictionary itself would be considered, but I guess it doesn't. No.
No, the strings are immutable in C#.
Okay, so yeah, the strings and the card array both being immutable. I thought that would therefore make the dictionary itself considered immutable, but
no,
that is definitely an assumption I haven't checked.
Yep. So, right. So now, also because this is a struct, in C#, every struct has a empty constructor, which really puts it into an invalid state. You probably don't want to do that unless you really need it for performance reasons.
Right.
But it's probably better to just have it as a class, because then this is an error.
I'm very much guilty of the classes everywhere mentality, so I'm not very good at when exactly a struct should be used.
So in general, you should use a class unless you have a good reason to use a struct. That's yeah. So we have this. Let's shuffle it. You have a shuffle method here. You don't really actually need this. What you can do is you can just say order by next.
I knew there'd be something, I could not find it. That's a lot cleaner.
Yeah, and then split. Let's take a look at the split. Yeah. So in our
and immediately, I know there's a problem here that I could not quite figure out. Of it cannot ensure the array has any size to it.
Yeah. So in C#, the only way to do that is to, because first of all, we can change this from being an array to being something more generic, because we can split anything that is enumerable into two parts. But then we also have to say this can fail, right? So it's, well, you can actually say maybe not this can fail, but let's do it like this. This can result either in an equal split, right? Or
with a remainder.
Yeah. And probably the best way to do this in our case here is we can take an enumerator, and then we can do it like this. We can take well, actually let's change these into the immutable arrays as well, just because we like immutability everywhere, or maybe immutable sequences. But in this method we can use local mutability, because that is often both more performant and even more understandable as well. The nice part of it is that because it's local, its scope is very small, and therefore it's easy to understand. So the problem with mutability is that it gets out of hand very quickly. So it's understandable in the small scope, but when everything's mutable, when it's in the large scope, in the large project, then it suddenly becomes very, very hard to understand what is actually changed, when it is actually changed, etc., etc., etc. Does that make sense?
Oh, yeah.
Yeah, so let's just create two lists here that we're gonna put our stuff into. And then let's say this, while enumerator, well, we have an element, right? We can take that element, and then there's going to be two cases. We might have the second element, right? Or we might not have the second element. So if we have the both elements, we can just put the first element into the first half, and then put the second element into the second half, and everything's nice. However, if we do not have the other element, then this becomes our remainder, right? And we basically reached the end of the list. And then we can say, well, we have to return, so in this library, things are put into this prelude thing, static class, like these helper methods. And essentially what we have here is we have the right case. So we have, here's the first half, and let's convert it to the sequence. Here's the second half, and let's convert it to the sequence. And then the remainder is the first element, right? I think, yeah, we can do this. And if we break out here, then we can just say it's this other case. So basically, it's this case. So now this split function is honest. You know that if you give it any enumerable, it will return you either this or this case, but it will not discard any elements silently.
I did have to think a little while you were doing that on why it was a problem to split it the way it was before, where if it's an odd number, it just gives 1 pi or more. Since that is, when you ask someone to split a deck, if it's odd, they'll just do it that way implicitly. They don't need to be told. And I guess it's because this is assumed behavior that it would do that, rather than it being very expressive in that is what it does when it cannot split it in the way you would expect.
Exactly. This is the problem of, so when you're writing software in a big scale with a lot of people, these assumptions, like when you're writing software alone, everything's usually just fine, unless you are writing it for such a long time that you start forgetting things, and then the past you is a different person than the current you. But when you're writing the software with multiple people, people will assume many things, and if things aren't explicit in the, let's say, function names or in the type signatures, then you do not know what will happen. And we do encounter bugs like that. So for example, we were using a library, right? And there's a thing where you can say, please run this action after this many seconds. Well, not seconds, milliseconds, right? So the question is for you, what do you expect if you give it a 0 for the time, for the delay? What should happen?
You would assume it would do it instantly.
That's what I assumed as well. Turns out it throws an exception.
Not even it has a edge case for 0 where it means something different like -1 often does. It just doesn't work.
Yeah, so and this is the problem with exceptions and these special values as well. If you do not model it explicitly, then you have this problem where somebody says, you know, I even did not think, I didn't write any code because the delay was computed, but I didn't think of that, yes, I have to write some code that will handle it differently in the 0 case. I just assumed that, you know, if I'm gonna put a 0 to it, it will just run it instantly. But if you look at it through the lens of pure functions, right, then that type signature should have been an either or an option because it has a capability to fail. And then you would instantly see that, hey, it either returns some failure case or a handle to the timer. And you will say, oh, there's a failure case? I wonder where that is. So the same thing applies here. If you just have...
It's handling the error itself makes it impure by calling outwards to the larger program saying, hey, something's gone wrong.
Yeah, exceptions are inherently impure because a pure function can do only one thing. It can only return a value. Anything else, throwing exceptions, mutating anything outside the scope of the, function.
IO.
Yeah, printing to console, moving things on screen. That is, not pure functions. And we want pure functions because they are simple, they are easy to reason about. I don't need to know much about this. What you can then do for convenience, right? You can do something like this. You can say split and split and discard. And then you can say, yes, this does not return an either, it just returns a tuple. And then you can delegate that to this case, and you can say, let's match, and on one case, so this presentation mode is fun. Yeah, so on one case we have this case, and on the other case we just can return the same tuple. And now, you kind of know from the name what it's gonna do. Actually, you should write a documentation saying, as split, but if the enumerable is not of an even size, it will discard the remaining element. And this has a lot less, surprise to it.
You also now just have the options of working either way with that edge case between the two functions.
Yep. And here, this is also problematic because here, do you see what assumption you made here?
That is not 0.
Yep. So this should really be this. Right? And this is where these marker traits kind of come in. So what we have is, I'm gonna just write it, it's not gonna be functional, but for example, what we have in our library is we do have this and then you would have like and then you could define something like this, where you would say
I did try add non-empty to this and I couldn't figure out how to use it since language extension has non-empty.
It does. Let's try. Oh yeah, it has some predicate. So there's a couple of ways how to implement that kind of encoding, but I'm not terribly familiar with language extensions per se. But we can, let's say, I'm just gonna show the idea here. So now, yeah, the idea is that if you know that something is non-empty, then you can return an element always, and it's not going to be an option.
It's requiring validity into the method rather than giving the option of invalidity out.
Yeah. Again, just a note, these are not pure functions.
Oh.
Do you know why?
I don't think, is it, all I can think of is because it's using a mutable array.
Not because of that.
It's
So
long shot.
Yeah.
Oh, it's calling .next on random.
Yep. And what does that do?
It will modify RNG coming in.
Yep.
So now you have modified the input.
Exactly. The idea of a pure function is that it only depends on the inputs. So, if the inputs are the same, the output should be the same as well for all the invocations, which is obviously not the case here. So
if you called GetRandom back to back to back, you would get different results.
Exactly. So what this actually does, it is a side-effectful thing. So we should mark it as such, like this.
Because this is probably wanted side effects. You do want GetRandom to give you a different result every time.
Yes. But wanted side effects are still side effects.
Yes.
And essentially what you want to do is you want to split your code into these two worlds, where there's the pure world and there's the impure world, side-effectful world. And
when there is no mistaking one for the other.
Yeah. And you can use the pure world from the impure world, but not vice versa. So you can think
of course.
You can think of impurity being as a plague. It infects stuff.
Impurity spreads downwards.
Yep. So what you can do, you can say, let's just say,
upwards, I think, actually. I always get confused.
Okay, this works. And the same thing here. So essentially what you're doing is you're wrapping this piece of code in a function. And it is quite so it comes with a cost. The cost is that you have to allocate a closure. You have to allocate this function. And when in context of game programming, usually you cannot do this, especially not in the main game loop. So there are a couple of other approaches of tracking purity via annotations, let's say, or other things. But in general, when in C#, our current approach is you just basically do it by hand instead of using any of the compiler tools. Because of the performance constraints, you just kind of split things into these two pieces and you say, I'm just not gonna call them. So yeah, with the annotation, it would look something like this. So you would have, an impure annotation here. And if you would try to call this, and then it would just be like this, right? And then if you would try to call any impure function from a function that is not marked as impure, some analyzer would need to tell you that, hey, what you're doing is wrong. Like you can't do that. But this is also like a pretty standard way. You just wrap the thing into like a wrapper and you say, this is side-effectful. So that's that what f means.
Yeah, seems very clean.
Okay, let's then.
So that's all the extensions done.
Yeah. So now, now we have this. And in our case, we basically have this, which we know is supposed to be even, right?
Mm-hmm.
So again, we could, in theory, also do something like this. And let's say call this even, and then say, let's duplicate this and say anything that is marked as even, we know that we can split it in half, exactly in half.
So you cannot give it, I guess, well, technically invalid input.
Yeah. And in this case, you would go like, something like this.
Although this now makes it impure, yes?
Yes, but so this is the trade-off. The trade-off is when the language doesn't have all of the tools that you need to write this, very safe code, then you say, if this contract is upheld, right? Then this will never happen. You could call it impossible, right?
No one should ever see this code. It's just in case of emergencies.
Exactly. And it is how C# actually works in a lot of cases as well. Because, for example, what you can do is you can compile your code having one library and then run it and exchange the DLL into another DLL, which doesn't have a certain method in it anymore, like the newer version of a library or older version of a library. And then your .NET Common Language Runtime, when running it, it loads that DLL dynamically, and then it will say, I expect to find a certain method on it, and there will be no such method, and then it will throw an exception saying, method not found, or no method, or something like that. Can't find it. Anyway, there's like a method, thing like that. So the idea is that there's a bunch of edge cases that are very, very rare. And for those edge cases, well, technically they should be, if everything is going according to plan, they should never be there, right? But for those cases, you can use exceptions because there's not much you can do except for, say, well, things have gone wrong. So you can think of it you can think about this from this standpoint. There's errors that you expect, and then there's errors that are truly exceptional. So errors that you expect and you can recover from, but errors that are truly exceptional, you cannot recover from. And there throwing an exception makes perfect sense because there's not much you can do. And no one will be catching that exception as well.
Yeah, no.
So yeah. In our case, we also need to probably do this. just to make sure that we can mark this as a covariant. And then we can say, oops, this is not Scala. Because where was it? Here. Yeah, we need to make this covariant because otherwise something that implements iEnumerable but is not exactly iEnumerable will not be accepted by this split method. So,
Right.
So yeah, and then we can basically say, so I think this implements iEnumerable. Yes, it does. So here you can say, you know, this is a marked thing, and yes, this is even. And then let's create another tool. So let's create a little helper. I guess that would. And this is a little trick that we've come up with. To not specify both of the generic parameters. So when you have this, then you're gonna say, I want to mark this, right? But then you would need to specify both of these. Or, so that's one way to do it. You can do it like this, right? Or you can alternatively use it like this. You just give an example value for the marker, and then it infers this part.
Right.
So, a tiny trick. Yeah. Again, this now suddenly has this problem where because of this encoding, we cannot order it properly, right? Because now it's marked instead of enumerable. So for that case, we also need to kind of add this method called transform. And if we look at Unity context, Unity really, well, IL2CPP really doesn't like extension, well, not extension methods, interface methods that take generic parameters. So we could try to do it like this. We can say we're going to be returning this. And let's call it transform and save, and give it a generic parameter. And then this takes a function from the data to data2. And we could implement that and transform it. However, from the Unity standpoint, from EL to CPP, it really has problems generating this code from the EL to CPP. So what you want to do is you want to put it as an extension method. and then say provide an implementation and basically do this. Now it's called unsafe because it's up to you to ensure that the marker still applies. And unfortunately, well, you could provide things like, let's say, shuffle for the specific combinations of markers. So it depends on what types you use mostly, but generically in a library fashion, you would have this. And then you would be able to say, okay, I know that I can do this. And shuffling the deck is preserves the amount of cards, and therefore this even marker will still be there, right? Again, this part is effectful, right? Because we're doing the random stuff. Essentially, we can probably start writing it from here, and we say, you know, the first effect is creating the random number generator. Do you know why it is side-effectful?
The creation?
Yeah.
Not off the top of my head, no.
So if you create two random number generators, right? Will they give the same numbers or different numbers?
I'm going to presume not. I haven't delved much with seeded random, but that does sound like the sort of behavior would have.
Yeah, so if you actually go here, you can see that there's this very, very weird stuff here going on. So what it actually does, first it inspects whether you extended it or not. So if you are instantiating something that extends random, then you're gonna get this implementation. Otherwise, you're gonna get this implementation. And then, you know, for this implementation, it's just gonna get some random bytes when instantiating it. So every time you instantiate it, you will get different random bytes. Therefore, it's not pure. And for this, again, this has like some shared random from which it takes a number which then is used as a seed. So see, there's a lot of funky stuff happening in the background, and this is definitely not pure. Then selecting the trump is also not pure. So we can do this as well, right? And this is the way that you compose these programs, these effects one with another. So basically what this says is I'm first gonna do this effect and then I'm gonna do this effect. And then I'm gonna do something else. And for us, that something else is we're gonna create this player. And we're gonna create this other player. And then we need to do this effect, which is shuffle deck. And then we can say why? Oh, come on. Yeah, C# type inference sometimes is so much fun. Wait, so this... Yeah,
Thankfully it's broken enough. I'll just assume it's broken as the first problem.
So now it will say cannot convert an array to IEnumerable. Great. Okay, we can, I guess we can just keep this as IEnumerable and then it works. Yeah. This also doesn't work. Unfortunately. So, yeah, these are not needed. But the idea is, yeah, we have the first player cards, right?
Mm.
And then we have the second player cards. And then we can say we can render this into the console, which is also a side effect, right? This is sort of a sin as well. So the problem is everything in C# has toString, which is fine if you're using it for debug values, but it becomes very not fine when you actually care about the output. And the problem is that wait, something. Why does it say this is an effect? Oh, right, this already, we already have this thing. Yeah, and now it says, yay, we have this, so probably we want to do something like this. Actually, this should be probably a set. Right. So yeah, and here we have all of the suits, and we know that it's a non-empty list. So then we can use that knowledge to get random. But again, we have this problem where our get random, well, in our case, it's also problematic because you cannot access sets by the index. So let's just turn this into an array. But again, we take a look at this, and we've only defined this for the regular arrays, not the mutable ones. Let's define it for these arrays. All right, I think again this should be I marked. Yay! So it takes some effort to actually, when you have a project, when you have a program, when you have a project, it takes some effort to actually build this whole infrastructure to make it ergonomic for the developers. But after you do that, it all becomes a lot easier. Because now you know 100% that this will never fail.
Yeah. As we covered, some of that like marking and stuff can be optional. You can just return like it could be incorrect and leave it at that.
Yep. Alternatively, you could do something like, this, and then just kind of throw here, say I'm gonna get an option here, and then I think there was some I don't know if this library has it, but in our library we basically have this get or throw thing. So
So if it cannot get it, it throws an exception.
Yeah, like it's reserved for the users where I've checked it in one line above. I cannot prove it statically, but I know that it should work just fine.
Yeah, one of those errors again that you should never see.
Yep. Okay, so we can take a look at this. Okay, I think this can be just enumerables, which also has this. So yeah, here with zip, right? This has the problem of what do we do if these decks are not of an equal size?
Right. I suppose that either needs to be sort of forced validity, or it must just return an exception.
Again,
or you could sort of imply the behavior of only do it to the smallest count, but that's still sort of implication there.
Yeah.
Edge case behavior.
So you want to be explicit in these cases, and the general strategy is if you can restrict the input arguments to such a form that it's impossible to call it with things that you don't want, right? So if you just say this, suddenly you do not have to zip it. You can just select, right, and apply this. Well, Actually, we don't really need this as well. You can just return this. And as well, you can, so previously it did it in parallel. So in theory, yeah, you can do that in parallel as well, because this only works on each element separately.
Right. So that also provides a solution to the problem happening in, I believe, another function around here, which has a switch, where I had 3 different arrays going by index. It's above these. Yeah, this one, where there's the deck 1, 2, and the winner array, and zip doesn't work for that. So managing to combine them into tuples, suddenly you can still just use select.
Yeah, so the idea here is you just take the cards and then you put them into different places. So yeah, we can rewrite that into just a tuple. And just do this. And this whole thing also becomes a very easy thing to do. So you're using internal mutability here, but let's kind of do it in a purely functional way. So we can use the aggregate function, which is also known as fold left in the functional world. And you can say, so we start with something, and that something is basically we have these 2, right?
Mm-hmm.
Actually, let's do it like that, yeah. So this is the initial state, right? And then you say, you get the tuple, and then you get the current state. I always mix the arguments, but yeah, it's like this. And then you can say, okay, so let's switch on the winner. Let's add a missing arms. And then if the winner is player 2, then let's return, so the player 1 score is kept as is, right?
Mm-hmm.
But the player 2 score gets both of the cards. Now a similar thing happens to if the player is player 1, right?
Mm-hmm.
And if we have a tie, everybody gets their own card back. And this one is, yeah, it's an default case. So there's that exhaustive matching plugin that you can add to your solution, and then it will become a compile time error instead of a just runtime error. And it's especially useful when you have these switches, and then you go and you add another case to here, and the compiler tells you, go to all of these places and fix it. Instead of, having a runtime errors. But for now, this will be just fine. So yeah, when you have this, then you can basically just do this and say that you have these 2 They're not arrays, they're sequences, but that's it. Does this make sense? Any questions?
Yeah. I will have to look a little into what aggregate is doing in my own time.
I can explain that. It's very easy. So what it does, it has some current state, which you give it. It's an initial state, and this is the initial state. So you basically say we have two score piles, and they're both empty. And then it starts from the beginning of the enumerable, and it takes an element, right? And then it runs this function. This is the element. So it takes this element, it goes here, and this is the current state that on the first iteration is this. And then you return the next state. So again, a value of this type. And then it does that with the second element, with the third element, etc., basically aggregating all of the elements into a single value.
Gotcha.
You could think of it like you have this thing, and then you take a part of it and you fold it, and then you fold it again, and then you fold it again, and again, and again, and again, and then you have this
nice allegory.
single value.
Right. Okay. That makes enough sense. Yeah. So that's effectively doing a lot of what was done previously with those internal mutables, but a lot cleaner.
Yep.
Same sort of idea. Okay.
Yeah. So this
these are why there's the winner enum, is because they started out as just comparers. So I built the sort of winner enum around that to be a bit more explicit.
Yep.
Expressive, rather.
Yeah. So these are like this, separate. But again, I'm gonna show you a bit of you can write a bit of a machinery to help out in this situation, and so you reuse it in your later code. So essentially what this does is you have this. You first compare this, and if the winner is tie, then you do this comparison. So let's do our own thing. Let's call it CMP, which is a shorthand for comparer, right? And let's say basically we have this enum, and let's call it compare results, and it has three cases. So lesser, equals, and greater, right?
Right.
And then you say, okay, so this is a comparer for type A, and when you compare something of type A, you will get a comparison result, right? Now when you have this, you can say, let's call this ICMP, because we need the static class, so we need a way to create it, right? And we can say we can provide one implementation. Let's call it lambda CMP, and it implements this. Essentially what it does, I think we can even make it record here, and we're just gonna take a function which does that, and we're just gonna invoke that function. And then we can say from compare to, which is the default C# comparison thingy, right?
Mm.
And that will give us ICMP for it. And again, we're gonna take a function, but this time we're gonna do this. And then we create this, we say compare to. We give it these two things. We also want to have a way to create the compare result. So we say, let's switch on this. So if this is this, then it's this. If it's zero, right, then it's equals. And in other case, it has to be greater.
So now we've effectively recreated the comparer class, but a bit more expressive since it's not just returning ints.
Yep. To be frank, I don't understand why somebody thought it's a great idea to use integers as comparison results instead of this.
Yeah, magic numbers.
So yeah, and then we can probably just as well do this other thing.
I imagine it's useful in terms of branchless stuff, being able to just multiply by the returned thing, but it's still branched plenty, so yeah.
Yeah, maybe. Then we can do this thing. As compare result. Can define an extension method. And here we can then say as compare result. So we have this, right? Then we can again create a little bit of abstraction for it. And say, so we need a way to do two comparisons, one after another, right? So that's essentially what you're doing there.
Right, okay.
So you can say...
So by sort of remaking comparer, we can now extend it even better.
Yeah. Well, there's already iComparer in C# standard library, but I dislike it because it returns numbers instead of these.
Yeah.
So
I didn't realize. Oh, yeah, it makes sense.
I guess we can actually let's. I'm not even sure. I mean, we could make this extend this. Yeah, the standard one, and then it has this, and we can just delegate to compare, and also say but this takes in nullable things as well. So you're like, why are these nullable? I don't know. In our case, we don't want anything nullable. If it's declared as non-option, it's not optional. So we can then say here's the first comparer and here's the other comparer, right? And then you can say let's compose these two. And you first try to compare these two results and see what happens. And if they're equal, then let's compare by the second comparer, right?
Would it being on equal not be assumed behavior rather than a specified result then triggering the next one?
Sorry, what?
With it calling the and then on that second CMP2 only on equals rather than on a specified one, isn't that then assumed behavior?
Well, it's what this combinator does. It's literally its purpose. So compares it basically it creates a comparer that tries to compare with CMP1 and then falls back to CMP2 if CMP1 returns
so this method would be inappropriate if you wanted it to fall back if it was, say, lesser.
Yeah. I mean, you could probably have a combinator like that as well defined, but in our case we don't need it. So
no.
You could probably add a parameter here like fallback on or something like that. But in our case, this explicitly does only fallback on equals. So this is also a bit annoying because you have to explicitly bind the result.
You want to use the old style of switch.
Yeah, you can't do this. So yeah, that's one thing. And now you can combine these two comparers together. And then you can also have this transformation. So you can, let's call it contramap. You basically say you say if you have a comparer for the, let's say, let's call it part and whole. So essentially you have a card which is comprised of two parts, the suit and the rank, right? And then you want to, if you have a comparer for the rank, you want to then be able to turn that comparer into a comparer for the card, which compares the card by its rank. So what we do is basically we extract, okay, you can call this extractor. You extract the parts from the wholes, and then you compare with the comparer that you already have. So now when you have this, okay, that's interesting.
I don't use the namespace anywhere, so it gets annoyed when it creates one.
So now when you have this, you can suddenly say, so we have this rank here, right? We can actually turn that rank into, so what we could do is we could assign a numerical values like this, but we tend to only do this for serialized data, because you might need different numerical values in different contexts. So instead we would just define an extension method. And then manually do a switch over it.
So since it now does effectively have both bits of information, how is this now more appropriate than the record before that stored them together?
What does have?
Before at the start, when rank was a record containing a value and the name.
Yeah.
This is now effectively that in a very different way, where you have the name as the enum, and you can use a function to get value just through a switch.
Yeah. So one of the things, for example, for the name part, you can consider about localization, right? Previously, the name was hard coded into the value, right? And if you wanted to suddenly localize your app, then it's problematic. Now the actual names can be stored somewhere else and be resolved based on the settings of the user or something like that. Again, in our case here, we do have this as integer. But if we would need to use that rank in some sort of different context, let's say in some games, this ace actually goes here. So it's the lowest card, or it could be both the lowest card and the highest card, you know. Previously, like if we put a value like this into the rank, it assigns information and it says this is the only possible way that you can look at this rank. But think of it this way. If you take an actual physical playing card, right? There's no intrinsic value described on it.
No.
That's
That's why it was then a static class assigning the value, which can then be, you can alter that behavior, you can substitute in different behavior. The record itself only just stored the 2 bits rather than assigning them directly.
But the record stored the number, right?
Yeah,
And
I suppose
string.
that would then mean you need different per game, a different set of cards. That's, yeah.
Yeah, so that's...
You can define the value, but once you have defined the value, it cannot change.
Exactly. Think about... Let's imagine this situation. So you have some wonky rule suddenly in the game where you're playing the game, right? And in the middle of a game, suddenly all of these ranks become different. Like not the cards become different, but the 7 is now worth 0, right? But only 7. You get a different rule set.
And the moment you've created the cards with the value is no longer intrinsic.
Yep.
Sorry, it is now intrinsic, as opposed to the rule set defining the value. It's sort of an inversion of that.
Exactly. So there's a really fine line between separating out what is intrinsic to the definition of the data, to the definition of the object, and what is actually an extrinsic part, sort of perception of some game or some players or whatever. And discovering this separation is a bit of an art, to be frank.
Yeah, I should have caught this one because the Scala review had the same issue but in a different form.
Yep. So it's like the same thing where you have a person, right? And then you say you model it by saying this person is a student, and you know student extends person or something like that. And then you say, oh, there's another branch which is called a worker, and it also extends person. But then you realize that the person can be both a student and a worker and a mom, and it can fill multiple roles, and inheritance isn't a great way to model it. And then you realize that a person, well, a person has a certain intrinsic value, as like your height is very intrinsic to you, or how many arms you have, or you know, other properties of your body and soul. But what kind of role you perform in the society, that's very fluid and can change very quickly. And especially when you're talking about immutable data, when you want to change something, then you would have when you have to change something intrinsic about the object, then you would have to go everywhere and find where that object is and do the change, which is easy in the mutable world because you go into the object and you just mutate one value. But at the same time, the immutable world forces you to think more about what belongs where.
You now must do more of the joyous world of composition over inheritance.
Yeah. And like, for example, the same problem here is, let's say you have this record game, right? And you have like a, I don't know, building. And this has like HP, right? And should this be a part of the building or not? Like, should the coordinates be a part of the building?
See, it feels like it makes sense to say yes, but technically that's just it happens to have its existence. It's not an inherent part of what makes that building that building.
Yep. And then the way you should model it is you have this, and then there's like some sort of map in the game where the buildings are stored, right? And especially if you store it here, you will probably still want this for fast access, right? But then there's a question, so what happens when these two are out of sync?
You now have invalid data, which is going to cause problems.
Yeah, and by not having these coordinates as a part of the building, you're removing that edge case. It's now impossible to have them out of sync. Okay, so let's go back to, right, we wanted to define, so we have this, and then we can say, so these ranks kind of have an intrinsic way of comparing them in our case with this as integer method, right? So we can just define a comparer. Well, actually we can even do this. We can say, let's define comparer for integers. And now when we have this, we can say here's how we define the comparer for the rank, by just taking a comparer for the integer and giving a function that turns rank into an integer. Make sense?
Yeah.
Now the suits do not have any intrinsic comparison, but we can create comparison for it if we know which one is the trump, right? Come on. So yeah, if both suits are the same, then they're equal. Else, if the first suit is the trump, then it's greater. Elsewise, if the second suit is the trump, then it's lesser. Else, these things are also equal. So now we have this, the way to compare this stuff.
Yeah.
And essentially what you can do now is you can say, let's create a comparer. Oh, we also need the comparer for the cod. So we have this. And we can say, first we compare by the trump. we turn that into a compare for the card. And then if that is equal, we take the rank compare and also turn that into a comparer for the card. So yeah, it is very similar to what you did. Where was it? Where you did here, what you did here, right? Except here you kinda do it with this. So basically you write a custom function that does everything that you want it to do. Whereas in our case, this is reusable and it is composable from tiny pieces. So you have these little tiny pieces which then you can, connect together like Legos and get the desired functionality. And you could even do this in runtime. So what we can do here is you can say, essentially you have this compare deck, and now you don't really need the trump here, just need a way to compare cards, right? And then you say, let's compare the first card with the second card, and well, we need to turn that into winner. So let's turn that into winner. And if the first player card is, so this is winner 2, and this is first.
Should be able to make it castable between the two types.
Yeah, but that's the thing. You don't want to cast it. Casting in general is a terrible idea usually. The only places where it is acceptable to cast things is where the conversion is how do I say it? Well, it does not lose information. So essentially, I'll probably tell you why casting is a bad idea here.
Well, I just remembered. Yeah, that only works as if you always compare player 1 to player 2, and not the other way around.
Yes, that's one reason. Another reason is by casting it, you just basically say, I totally know that the values of these two enums are gonna be related, but nothing in the code actually enforces that. If somebody goes and changes, these values here,
They add a player 3.
Yeah. So there's like a lot of possibility for breakage. Whereas in this case, you explicitly say, I do a comparison, and this is what this comparison means in this particular case. And this is, so this is a good way to do it. So basically you have some data, you switch over that data and transform it into some other data. And we don't need this anymore or that anymore. So now let's go back to the program and finish this. So we need the comparer for the trump, right? And we just create that. We do have this. We split the deck. And then we do, all right, this is gonna probably be annoying. Yeah, and this requires you to return something. So maybe there's like prelude, write, print, console.
Out?
No, I mean, just to not have this.
Yeah, seeing if it maybe uses the out wording instead.
Yeah, the problem is that in C# there's like two different things. There's an action and there's a function, and the function has to return something always, and an action does not.
You could use delegate.
Sorry?
Could use delegate since func and action. I don't know how it tries to convert between them, but delegate encompasses both.
No, so an action and a func are just two delegates.
Yeah.
Which
I might have misunderstood what you're trying to accomplish then, if that's not.
The point is that in, for example, let's say in a language like Scala, this, instead of returning void, this would return a unit, which is a value. And then you do not have to have this distinction between functions that return a value or functions that return no value, because you can always return a unit value, which only has one value, which is unit. And it's a type that only allows one value and holds no information. So it's basically an empty struct.
Right.
And then, you don't have to deal with this. But in our case, we do have to deal with that. Compare deck. So again, we did have this. We did have these players. I don't really think we need these players to be.
No, it's more. They were more there sort of out of obligation. They don't really do anything other than hold the decks.
Yeah. So we can probably just do this, player cards. And we split this in half. Yeah, so that's one way to do it. Maybe we should even have another method that returns the pairs, but something like split as tuples. And then we can zip here. And here we rely on the fact that we know that this will split into even halves. Well, not into equal halves. So then we can do this thing. Right. So we have, well, let's call it result winners, round winners. Although it's many rounds winners. And then we have this.
Where linguistics and code don't quite intersect.
Yep. Yeah. Then, yeah, here we also have this only winner. So we probably want to, in our case, we probably want to do this, right? Just because this method requires that.
Mm.
You can actually then say this. And then there's a bunch of printing here. I'm not sure, shall we go through it or not?
There's not much going on there. It's pretty much just looking through every run round, saying what the cards were and which one of those was the winner, which we already have computed.
Yeah, so
At the end, there is a bit of a funky compare going on, just saying who the final winner is.
So, what do you have here? Well, this is a bit overcomplicated.
Yeah, I realized after the fact it probably doesn't need to be a variable. Getting a bit carried away with that in function.
Yeah, you can just say, so let's put all of that. Well, actually, you would probably just, we have this, we have this. So essentially, I guess this is the final result of the game, right? The score piles. And it's an effect, and it produces these two score piles. You could as well return the intermediate stuff if you wanted to, but in our case, we basically have this thing, and then we say run, right? Which actually launches this program, because until you say run, it doesn't do anything. It's just a description of the program. And then you say, well, what happened when we ran it? And there's gonna be two cases. So there's the success case, and in that case, we do get score piles. And then there's the failure case. In that case, we get an error. So, you know, if bad things happened, we can do this and then say.
Right, so this is separating out the order calculation compared to the IO out.
Yep. And for
Would the trump suit not also then be a part of that? It's not really a big deal, so.
Wait.
Trump suit message rather.
Oh, this thing. Yeah, we can also probably just do this. And say, here's the trump and score piles. And here, yeah, you probably also want to return this as well, because you want to do here, the deck count is probably these round winners, right?
Yes.
Rank name. Yeah, so for our purposes here, for example, we should say show rank and give it the rank, and because we don't really care right now, let's just do toString for it. But you could do a pattern match on it and then do whatever you need there. And then oh yeah, actually you probably want to just have show card instead. And then have this. Oops. Let's call it C. And suit, C suit. Right, so split things into tiny chunks and compose bigger chunks out of those tiny chunks.
And now we can reuse anytime we want to show for some IO.
Yep. And then we have this, right? So, and this is It also becomes a lot more readable, huh?
Yeah, it's a lot less bulbous is the word that comes to mind.
Yeah, and here we just say so this kind of repeats itself. So we could extract this into a method and give it a good descriptive name and documentation, and then reuse it. But essentially,
the idea is clear.
Yeah, essentially this is what we have. So this becomes actually, so there's the pure part of the code, right?
Mm-hmm.
These things, and you can extract them into a separate method if you want, into a separate function if you want. This is the pure part of the code. This is the impure part of the code. And this is also impure part of the code where it just, does all of the printing. And what we can actually also do is we can say, we can actually turn that into a pure part like this. So we had this. We had this. And then we had this. Right. And we can take all of this jazz here, put it here. And instead of console, let's use the string builder. Instead of write line, it's append line. And we just have to return the string. Suddenly, this is also pure.
Mm-hmm.
So what you can then do, you can just say, I have this program, and then let's just bind it, and we're gonna get these results, and then we're gonna say, well, first you can just have this program which turns these results, then I'm gonna turn them into something that is, into a string, and then I'm gonna do another side effect. So essentially it's just gonna should really just introduce this. And then you can just use it like this. And now this is unit, which doesn't really do anything. So if we succeed, that's just fine. We have finished the program. So again, you can, this previously had side effects and computation intermixed, and we rewrote it so it became pure. And then you push these effects into kind of boundary, the edge of your program.
Is there any sort of notable downsides to taking all of that previously sort of throwaway strings and storing them into one giant string to be returned now?
So the downside is that this has to fit in the memory. Previously, it would write it to the console and forget about it. Now this has to fit into the memory.
Okay. So a trade-off, but not an awful one.
Yeah. If you do need, streaming, there's solutions for that as well. But then obviously, you can turn this into like an enumerable of strings, and instead of returning doing append lines, you can yield these things one by one on demand.
All right then. I think that's everything with this script. It's very much been transformed.
Yep. So, what are your thoughts?
I'm surprised just how far it was modified. I thought there'd be a lot of, small changes that added up, but not quite so radical changes in a lot of how it. Or they seem radical, but really a lot of it is still the same at heart.
True.
It's just a very different way of doing same sort of methods, albeit some of them manage to be compressed and improved a little bit, like adding in the and then and such.
Yeah. Most of what happens is, so a couple of things that has happened. When you have immutable pure function, when you have immutable data and pure functions, what you get is code locality. So you take a look at this, and you do not really care about anything except this function. You do not care that somewhere there's some mutable variable or something else. All you care is code in this function, and that's it. And same for any other part of the code. You take a look, and it's 3 lines, and you only care about these 3 lines, and that's it. The only thing, especially because this is static, so that's a very nice benefit of pure functions, that the context that you have to have in your head is very small. Another benefit is that we tried as much as we could. So there's obviously trade-offs, to all of this. But the idea is that you put information into the type system so that the compiler could check it for you instead of you having to check for it. And when you come down, later down the line, and you look at that code, you can read and understand things about that code, these invariants, these things that you knew when you were writing the code. Like, for example, that this deck is of even size, right?
Known truths.
Yeah. So if you come 1 year later and you take a look at this deck, and it looks like this, you have no idea, and you say, like, is it, how big is it? Is it of even size? Is it of
that
odd
truth
size?
is now just an implication that you would never make while any time after the fact.
Yep. So, and especially for these methods, extension methods that we wrote, that if you've proven to me that this is even, then we can split it into 2 equal parts, and there's no remainder, stuff like that. So these things really help when you're refactoring the code down the line, especially the code that you have written. So because you can refactor, as I like to joke around, you can still refactor while being half brain dead. Because you don't need as much thought to put into it than you would if there's no compiler catching the errors for you.
You no longer have to refigure out these known truths about all of these different variables that are made explicit.
Yeah. And probably the third part is by making sure that side-effectful code is by kind of introducing this this thing where it's not very fun to interact with side-effectful code, right? You have to write it in a different way, you have to compose it in a different way. We suddenly noticed that, hey, this can be non-side-effectful, right? And we extracted it into this non-side-effectful function, whereas previously you would probably just have the version where it both created the data and wrote it to the console at the same time and just left it.
Now it's been minimal amount of change to separate out those two different bits of behavior and make some of it pure.
Yeah, and pure functions are very easily testable. So previously, if you wanted to test this created string, you would have a very hard time, because testing something has been written to the console, well, not great thing. Now you just give it some data and you test what string it spits out, right? So these are the benefits that you get.
Yeah. And in doing it well enough, it's not suddenly such a problem to have all of the extra garbage generated by immutability.
So it depends. If we're talking about the context of the games, then yeah, there's places where you just can't do that and you have to rely on mutability, but that usually involves the gameplay code, and the gameplay code has this nice property of it being pretty local and pretty simple compared to, let's say, user interface code. So
yeah.
And some of the techniques are garbage free. So for example, not using nulls and using options instead, or not using exceptions and using ivers instead. Both of those are structs, so you do not allocate any garbage, and you can use them in the gameplay code as well.
All right. Yeah, that's yeah. There's a lot to keep in mind, but it definitely seems a fair trade-off.
Yeah. Okay, so let's wrap this up, and I guess for the viewers, see you in the next video.